Hello, everybody. Hello. Let me just simply get my Twitch chat out, pop out, and start with the tutorial. Hello, everybody. Let me make the pop out bigger. Yes. Hello, everybody. Hello, everybody. Yes, how does the stream look like on YouTube? View my channel. Let's see how view my channel looks like. Let's see how view my channel looks like. Let's see. Yes, it is fine, I guess. It is fine, I guess. It is fine. It is fine. We could simply start the transformations capital chapter section. Hello, how are you feeling today? Oops, sorry. Okay, you're okay, it's fine. I'm fine. Fine, thanks for asking. Thanks, and we're going to learn the transformations today. Transformations is not really about OpenGL, but generally about graphics programming. It's math, so we're just going to read through, and see what transformations there are. I'm not going to implement. Maybe I will implement. I don't know. We will see. Yes. Is my voice fine, by the way? Let me check that little quick. Little quick. Little quick. Little quick. Can you hear me? Little quick. Can you hear me? Yes, I can hear myself. Can you hear? We can start for real now. Yes. Okay. Transformations. Let's read from start to finish. We now know how to create objects and color them and give them a detailed appearance using textures, but they're still not that interesting since they're all static objects. Yes. We could try and make them move by changing their vertices and reconfiguring their buffers each frame, but that's cumbersome and costs quite some processing power because you have to transfer the vertices and stuff. And there are much better ways to transform an object, and that's by using multiple matrix objects. This doesn't mean we're going to talk about Kung Fu in the large digital artificial world. Matrices are very powerful mathematical constructs that seem scary at first, but once you'll grow accustomed to them, they will prove extremely useful. Disclaimer: I know about matrices already due to my education. Yes. When discussing matrices, we'll have to make a small dive into some mathematics, and for the more mathematically inclined readers, I'll post additional resources for further reading. However, to fully understand transformations, we first have to delve a bit deeper into vectors before discussing matrices. The focus on this chapter is to give you a basic mathematical background in topics we will require later on. If the subjects are difficult, try to understand them as much as you can and come back to this chapter later to review the concepts whenever you need them. Let's go. In its most basic definition, the vectors are directions and nothing more. So a vector has a direction and a magnitude, its length. You can think of vectors like directions on a treasure map. Go left 10 steps, now go for north 3 steps, and go right 5 steps. Here left is the direction and 10 steps is the magnitude of the vector. The directions for the treasure map thus contains 3 vectors. Vectors can have any dimension, but we usually work with dimensions 2 to 4. If a vector has 2 dimensions, it represents the direction on a plane because it's 2 directions. One direction is upwards and one direction is in the right direction, in the right. It can be left, right. It's not decided, but it's simply 2-dimensional, which means there are 2 and 2 only um, what do you call it, directions. And 3 dimensions mean you have 3 directions, 3 different directions. Below there are 3 vectors where each vector is represented with x and y as arrows in a 2D graph. Because it's more intuitive to display vectors in 2D rather than 3D, you can think of the 2D vectors as 3D vectors with a z coordinate of 0. Since vectors represent directions, the origin of the vector does not change its value. In the graph below, we can see that the vectors v and w are equal even though their origin is different. So v is defined through plus 0, 0, 0 plus 3, 2, and the v is defined through 3, 1, 1, 3 plus 3, 2. When describing the mathematicians generally prefer to describe vectors as character symbol with a little bar over their head, like v with a bar. Also, when displaying vectors in formulas, they are generally displayed as follows. V with a bar over their head has 3 elements which are called x, y, and z. Because vectors are specified as directions, it is sometimes hard to visualize them as positions. I mean, this is a concept that is a bit, you know, not so clear to all, because you display the direction also with 3, 2, but display the point also with 3, 2. See what I mean? I mean, there are 2 vectors, position vectors and direction vectors. You want to visualize vectors as positions, I mean these 3, 2 point, we have to consider the starting point the origin. Simply starting from the 0, 0, 0, if you move 3 to 0, we are then at the point E2, so we are describing this point, this position. If we if we specify a different origin, then we should say that this vector points to that point in space from this origin. Position vector 3, 5 here would then point 3, 5 on the graph with an origin of 0, 0. Using vectors, we can thus describe directions and positions in 2D and 3D space. It's like with normal numbers, we can also define several operations on vectors, like adding them together, subtracting them, and scalar vector operations. What is a scalar vector operation? it's simply adding a scalar value, or multiplying the vector with a scalar value, or dividing, or whatever you can call it. It works like this: if you want to multiply or add a scalar value to a vector, you simply add or multiply each element of the vector with the given with the um, with the scalar, which then yields another vector. And the negation is simply multiplying the vector with a scalar -1. Each component has a minus sign. Addition and subtraction between two vectors function component wise, meaning you add two vectors v and k. You have to add each component separately, meaning the result of this v and k would yield 1 plus 4, 2 plus 5, 3 plus 9, meaning 5, 7, and 9. Visually, it represents a triangle. You start on the origin point and move uh, move along the first vector, which is 4, 2, and after that you take this position as the starting point for the next vector, and you move 1, 2, meaning you are now at 5, 4. By with the subtraction, it works like this: you have to move this v vector, and thereafter have to you have to move sorry, what's this v vector? This is 0 0.5, 3.5. Thereafter you should move minus v, so you have to move like this, and -2 like this, and you will then find difference. In this case, doesn't do this, I suppose. So how we understand this? This is the v vector, and added with the v vector there is w minus v vector, and if we add them together, we will then get w vector like this adding. It simply is a different um, org organization of the vectors. And what is length? How do we retrieve the length of a vector? We simply we simply get the x component, for example, and y component, and then simply use the Pythagoras theorem, which means a quadrat plus b quadrat equals c quadrat, which in our case is the vector we want to find the length of yes. So we simply add x quadrat plus with y quadrat and get their square root. So this vector then has length of 4.4 and 7. So there is a concept called unit vector, and this unit vector is a vector that has the length of 1, and we can calculate the unit vector from any vector by dividing each of the vector's components by its length. This is called normalizing. And unit vectors are displayed with a roof over their head. Okay. How about vector production? What vector multiplication? What options do we have? We have the dot product, which is called as a scalar product, cross product, which is called dot product and scalar product. Sorry for the cross product is another thing. The dot product of the two vectors is equal to the scalar product of their lengths times the cosine of the angle between them. So this is a length, this is a length, and this is the angle between two vectors. This is simply the mathematical multiplication we are used to. We can call it 3 times 5 times I don't know what. This is the mathematical, this is the vector multiplication. The angle between them is represented as theta. Why is this interesting? Well, imagine if v and k are unit vectors, then their length would be equal to 1. If we normalize these vectors, v and k, we then have the cosine of theta of the between the two vectors. We simply can determine the angle between two vectors if we normalize them and find their dot product. Yes. Now the dot product only defines the angle between both vectors. You may remember that the cosine or cos function becomes 0 when the angle is 90 degrees or 1 when the angle is 0. This allows us to easily test if the two vectors are orthogonal or parallel to each other using the dot product. So if we get 0 or 1 here, we can simply determine if the two vectors are orthogonal or parallel at a right angle. Okay. I mean, orthogonal means that they are standing like this. Like this. There are 90 degrees between. In case you want to know, okay. You can also calculate the angle between two non-unit vectors, but then you'd have to divide the lengths of both vectors from the result to be left with cosine of this theta angle. So how is the dot product calculated? We simply get this and multiply with this and add this multiplied with this and add this multiplied with this. So we simply multiply each component with the corresponding component of the vector, another vector 2, and we then at the end compute the addition of the solutions that we get from multiplying the components. Then afterwards we have to calculate the reverse cosine function of the result to get the angle between two vectors. And we have another operation that is called cross product. Cross product is only defined in 3D space. It takes two non-parallel vectors as input and produces a third vector that is orthogonal to both the input vectors. So if we have vector k and a vector v, we can find the vector v cross k by simply calculating cross product of these two vectors, and this newly found vector v cross k will then in fact be orthogonal to the two vectors k and v we had. This will prove useful in the upcoming chapters to find three orthogonal vectors, and the image shows how that looks like in the 3D space. And unlike other operations, the cross product is not really intuitive without delving into linear algebra, so it's best to memorize the formula and you'll be fine, or don't, you'll probably be fine as well. I will not explain this. This is simply the formula, and use it to get orthogonal vectors. Matrices, what are matrices? Matrices, you can see the matrices as an array of numbers, symbols, or mathematical expressions. Each individual item in a matrix is called the element of the matrix. An example of 2 by 3 matrix is shown below. 2 by 3 matrices are indexed by E and J, and where E is the row and J is the column. That is why the above matrix is called a 3 by 2 by 3 matrix. If it were 3 by 2, then it would have 1, 2, 3, 4, 5, 6 in the columns. To retrieve the value for this value, we have to index the second row and the first column, so 2 and 1. Matrices are basically nothing more than that, just rectangular arrays of they do have a very nice set of mathematical properties, and just like vectors, we can define several operations on matrices, namely addition, subtraction, and multiplication. Addition and subtraction are pretty basic and straightforward. We simply add each element together, meaning we have 6, 8, 10, 12. Because we add 1 to 1 with 5, 2 with 6, 8, 3 with 7, 10, 8 with 4, 12. Subtraction is the same, and the scalar products are the same with the vector scalar products. Simply multiply each element with the scalar we have before, and the matrix multiplication is a little bit what do you call it, is a little bit complex because it has a unique structure to execute the multiplication. And how does it go? It goes like this. You can it has two rules, two first restrictions. You can only multiply two matrices if the number of columns, these two, match with the number of rows on the right hand side matrix. So if you have a 3 by 3 matrix, you can only multiply it with the matrices that have 3 rows. And if you have 1 by 90 matrix, you can only multiply this matrix with the matrices that have 90 rows, and the matrix multiplication is not commutative. So this is a bit weird for the non mathematicians, because each multiplications in mathematics in each vector, sorry, two scalars a and b are multiplicated. For example, 3 times 3 is also 3 times 4 is equals to 4 times 3. How does the matrix multiplication work? It works like this. You multiply this with this, meaning 1 times 5, 2 times 7, and you just add it. And after 1 times 6, 6 and 2 times 8, and you add it. Afterwards, you multiply 3 times 5, 4 times 7, you add it. And it goes on like this, and afterwards we have the 2 by 2 matrix again. I'm not going to read each. This is basically the same. You multiply this, and add it for the first and first. And afterwards you multiply this with this and this with this, and you add it. This is pretty straightforward if you think about it. It's at first a bit hard. It's a cumbersome process. I'm not gonna lie. It's quite time consuming. But if we can define the formula, then we can make it so that the program calculates the multiplication for us. And how does the matrix vector multiplication look like? The matrix vector multiplication is simply another form of matrix multiplication, but the vector we have is seen as n to 1 matrix, meaning we had a 3 by 3 matrix here, and if we have 3 by 1 matrix, meaning only the 4, 2, and 9 elements of the matrix are considered for a multiplication, we would then have a matrix vector multiplication. So this is basically the same. You just simply multiply this with this, this with this, and this with this, and add it together, and you get the first matrix. You get the matrix vector multiplication. And what is an identity matrix? An identity matrix is a matrix that does basically nothing to the another matrix or to the other vector while calculating the multiplication. Simply returns the same value of the matrix or the vector. What is scaling? Scaling is altering the length of the vector. This does work in this works by changing the identity matrix with the scaling factor we would like to use. So if I want to scale the matrix 1, 2, 3, 4 by simply say by half. If I want to divide by 2 each component, I would simply type 1.5 here, 1.5 here, and 1.5 here, and 1.5 here. So I just scaled the matrix length to just scale down the matrix length, vector length, sorry. This changes the length and the orientation of the matrix. Orientation of the matrix, and this is simply the scaling matrix. We can define it simply by using 3 scalar values called S1, S2, S3. because we only and only we only and only um, alter the values of the identity matrix. And what is translation? Translation is the process to moving the vector on top of the original vector. So if we wanted to move v3 to 2 to another place, we would have done a translation. This translation matrix also translation also can work with a matrix multiplication by using this translation by using the translation matrix, and the translation matrix can be defined using three scalar values that are called tx, ty, and tz in our case. And yes, this follow the resulting vector is then x plus tx, y plus ty, and z plus tz. This is achieved by using homogeneous coordinates. I'm not going to dive deeper into this because I don't want to explain a lot about linear algebra here. Could study on it later. This is simply adding another vector here, another scalar here to the three-dimensional vector to achieve this. Yes, whatever. A rotation. Rotation is rotating a vector in an angle around an axis. Yes. How are these matrices are how these matrices are created? You can find videos on this about on YouTube. And yes, what do we want to create it? I actually don't want to delve deep into this because there is a library called GLM, and this GLM simply I want this. What is this? GLM is an OpenGL mathematics library. It has built-in GLM rotation matrix. So if you want to create another matrix like this, you should simply use that method. And this is also pretty straightforward. If you want to rotate around the x-axis, you should simply define this matrix here by specifying the degrees or radians you want to rotate, and it will rotate this around the x-axis. Yes. And there is another matrix which is created by combining these three matrices, and this is called, I think Euler rotation matrix. I don't know anymore. You could simply create that or use the GLM mathematics library. There is something about quaternions here. I'm going to read it. Using the rotation matrices, we can transform our position vectors around one of the three unit axes. To rotate around an arbitrary 3D axis, we can combine all three by first rotating around the x-axis, then y-axis, and then z-axis, for example. However, this quickly introduces a problem called gimbal lock. We don't discuss the details, I'm just going to note it, what the gimbal lock is. But a better solution is to rotate around an arbitrary unit axis. Note that this is a unit vector right away instead of combining the rotation matrices. Such a verbose matrix exists and is given below with Rx, Ry, and Rz as the arbitrary rotation axis. A mathematical discussion of generating such a matrix is out of the scope of this chapter. Keep in mind that even this matrix does not completely prevent gimbal lock, although it gets a lot harder. To truly prevent gimbal locks, we have to present rotation using quaternions. that are not only safer but also more computationally friendly. However, a discussion of quaternions is out of this chapter scope. So this chapter simply achieves but the basic stuff. How do we combine matrices? We simply multiply them. That's all. And afterwards, we run the final transformation matrix with our position or direction vector. In practice, we use GLM, OpenGL Mathematics Library. It is a header-only library, which we should only include the proper header files, and we are good to go. How can we translate a vector 100 by 110 by using OpenGL mathematics library? Is simply uh, we we have a vector 100 that is a direction vector. Let me see if direction vector. Homogeneous coordinates. Coordinate. Direction. I need to check this one time. The homogeneous coordinate is xy1 is supposed to be a position vector, and the direction vector is x minus 0. So this is a position vector. We created. Sorry. We can create a translation vector by creating a matrix, identity matrix, and afterward simply say want to translate this matrix. We want to create a translation matrix that translates by this amount. And afterwards we get a translation matrix and simply multiply our vector with this translation matrix. We translated matrix. What is this? Rotate and scale. What it does? It rotates the rotation translation matrix, and it scales the transformation matrix afterwards. So it first rotates and afterwards it scales. This should rotate and scale it down because we are using 0 0.5, 0 0.5, 0 0.5, and the texture coordinate doesn't change, and the GL position is simply determined by multiplying the position with the transformation matrix. And the transformation matrix is a uniform matrix, so it is said it is a uniform matrix for FV. Like I said, I will not implement these. And the rotation works with the time here, translated and rotated, so it should translate down. Okay, and it should rotate. Yes. Yes, I am done. Transformation and move on to coordinate systems. I will take 5 here, I guess. Need to get some water. Something. Yes. Be right back. Hello back. Hello again. Sorry. Let's see who is watching it. There are no people watching it stream right now. No? Yeah. How does the YouTube look like? I'm watching. No, I don't care actually. Yes. Coordinate systems. The next chapter, next section of our tutorial, we have only the camera section left. Before we are ready. Before we got started. Before we finish the getting started chapter. We will simply, if I can put through, I will end it today, the getting started chapter. Let's see. And this is a bit longer chapter, it seems like. Let's read it. In the last chapter, we learned how we can use matrices to our advantage by transforming all vertices with transformation matrices. OpenGL expects all the vertices that we want to become visible to be in normalized state device coordinates NDCs after each vertex shader run. That is, x, y, and z coordinates of each vertex should be between -1 and 1. Coordinates outside this range will not be visible. What we usually do is specify the coordinates in a range we determine ourselves and in the vertex shader. Transform these coordinates to normalized device coordinates. These NDCs are then given to the rasterizer to transform them to 2D coordinates / pixels on our screen. Transforming coordinates to NDCs is usually accomplished in a step-by-step fashion where we transform an object's vertices to several coordinate systems before finally transforming them to NDC. Advantage of transforming them to several intermediate coordinate systems is that some operations / calculations are easier in certain coordinate systems, as will soon become apparent. There are a total of 5 different coordinate systems that are of importance to us: object space, world space, view space, clip space, and screen space. Those are all at a different state at which our vertices will be transformed in before finally ending up as fragments. Local space, model matrix, world space, view matrix, view space, projection matrix, clip space, and afterward screen space. The following image displays the process and shows what each transformation does. The most important matrices are model, view, and projection matrix. Local coordinates are the coordinates of your object relative to its local origin. They are the coordinates your object begins in. The next step is to transform the local coordinates to world space coordinates, which are coordinates in respect of a larger world. These coordinates are relative to some global origin of the world, together with many objects or many other objects also placed relative to this world's origin. Next, we transform the world coordinates to view space coordinates in such a way that each coordinate is as seen from the camera or viewer's point of view. So in this case, the camera is in the upper part. Yes. After the coordinates are in view space, you want to project them to clip coordinates. Clip coordinates are processed to the -1 to 1 range and determine which vertices will end up on the screen. Projection to clip space coordinates can add perspective if using perspective projection. And lastly, we transform the clip coordinates to screen coordinates in a process we call viewport transformation. That transforms the coordinates from -1 to 1 to the coordinate range defined by GL viewport. The resulting coordinates are then sent to the rasterizer to turn them into fragments. You got probably got a slide. The reason we are transforming our vertices into all these different spaces is that some operations make more sense or are easier to use in certain coordinate systems. For example, when modifying our object, it makes the most sense to do this in local space, while calculating certain operations on object with respect to the position of other objects makes most sense in the world coordinates and so on. If you want to, we could define one transformation matrix that goes from local space to clip space all in one go, but that leaves us with less flexibility. We will discuss each coordinate system in more detail below. Local space is the coordinate space that is local to our object, where our object begins in. Imagine that you've created your cube in a modeling software package like Blender. The origin of your cube is probably at 0, 0, 0, even though your cube may end up at a different location in your final application. Probably all the models you have created all have 0, 0, 0 as their initial position. All the words of your model are therefore in local space. They are all local to your object. The vertices of the container we have been using were specified as coordinates between 0.5 and 0.5 with 0, 0 at its origin. These are local coordinates. If you would import all our objects directly in the application, they will probably all be somewhere positioned inside each other at the world's origin of 0, 0, 0, which is not what we want. We want to define a position for each object to position them inside a larger world. Coordinates in world space are exactly what they sound like. Coordinates of all your vertices relative to a world. This is the coordinate space where you want your objects transformed in such a way that they are all scattered around the place. The realistic version, the coordinates of your object local to world space. This is accomplished with the model matrix. So model matrix transforms the local coordinates into world coordinates. The model matrix is a transformation matrix that translates, scales, and rotates your object to place it in the world at the location/orientation they belong to. Think of it as transforming a house by scaling it down, translating it to a suburbia town, and rotating it a bit to the left on the y-axis so that it neatly fits within the neighboring house. You could think of the matrix in the previous chapter to position the container all over the scene as a sort of model matrix as well. We transformed the local coordinates of the containers to some different place in the scene or world. View space. What is a view space? The camera. Is the camera space, eye space. The view space is a result of transforming your world space coordinates to coordinates that are in front of the user's view. The view space is thus the space as seen from the camera's point of view. This is usually accomplished with a combination of translations and rotations to translate/rotate the scene so that certain items are transformed to the front of the camera. These combined transformations are generally stored inside a view matrix that transforms world coordinates to view space. The next chapter will extensively discuss how to create such a view matrix to simulate a camera. At the end of each vertex shader run, OpenGL expects the coordinates to be within a specific range, and any coordinate that falls outside this range is clipped. Coordinates that are clipped are discarded, so the remaining coordinates will end up as fragments visible on your screen. This is also where clip space gets its name from, because specifying all the visible coordinates to be within range -1 to 1 is really intuitive. We specify our own coordinates set to work in convert those back to NDC as OpenGL. Transform vertex coordinates from view to clip space. Define a so-called projection matrix that specifies a range of coordinates, e.g. -1000 and 1000 each dimension. The projection matrix then converts. Where did it go? Here. Converts coordinates within this specified range to normalize the base coordinates -1 to 1. Directly a step called persective. Whatever. All coordinates outside this range will not be mapped between -1 and 1 and therefore be clipped. Within this range, we in the projection matrix a coordinate of 1150, 500, 750 not be visible since the x coordinate is out of range and thus gets converted to a coordinate higher than 1 point and is therefore clipped. Note that if only a part of the negative triangle is outside clipping volume, I will reconstruct triangle as one or more triangles. Clipping range, okay. The viewing box is a projection. Viewing box, a projection, is called a frustum, and each coordinate that ends up in the frustum will end up on the total process to convert coordinates with wide range. See that can easily be mapped to previous coordinates is called projection. The projection matrix projects 3D coordinates, so easy to map to the normalized device coordinates. Once all the vertices are transformed to clip space, final operation called perspective is performed, where we divide the x, y, and z components of the position vectors by the vector's homogeneous w component. Perspective transforms the 4D clip space coordinates to 3D normalized device coordinates. This step is performed automatically at the end of the vertex shader step. It is after this stage where the resulting coordinates are mapped to the screen coordinates using the settings of GL viewport and turned into fragments. The projection matrix to transform view coordinates to clip coordinates usually takes two different forms, where each form defines its own unique frustum. We can either create an orthographic projection matrix or a perspective projection matrix. I'm not going deeper to the orthographic projection and perspective projection. Perspective projection is what we are used to seeing in the artworks. It's the more of a real life, and this is for the what I would say simulations. I would say this is more true, more scientific. Yes, how do we create a projection matrix? We simply say GLM perspective. Is this out? Now let me read perspective projection. What it has to say. This is a long chapter. No, not that long. Let's read a perspective projection. If you ever were to enjoy the graphics the real life has to offer, you'll notice that objects that are farther away appear much smaller. Of the perspective. The 3D effect is called something we call perspective. Perspective is especially noticeable when looking down the end of an infinite motorway or railway as developing smaller. As you can see, due to the perspective, the lines seem to coincide at a far enough distance. exactly the effect perspective projections tries to mimic, and it does so using a perspective projection matrix. Projection maps a given range to deep space, but also manipulates the v value, w value of each vertex coordinate in such a way that the further away a vertex coordinate is from the viewer, the higher this w component becomes. Once the coordinates are transformed to Cliff space, they are in the range minus w. w. Anything outside this range is clipped. OpenGL requires that the visible coordinates fall between the range -1 and 1 as the final vertex shader output. Thus, once the coordinates are in clip space, perspective division is applied to the clip space coordinates. Component of the vertex coordinate is divided by its W component, giving smaller vertex coordinates the further away the further away a vertex is from the viewer. This is another reason why the W component is important, since it helps us with perspective projection. Resulting coordinates are then in normalized device space. If you are interested to figure out how the orthographic and perspective projection matrices are already actually calculated and aren't too scared of the mathematics, I can recommend this excellent article by Sonko. Article. Let me save this. Can be created in GLM as follows: radians, float width, divided by float height, one function. Please, come on. Come on. GLM perspective. The function GLM perspective creates a perspective projection matrix from the given parameter. The actual mathematics behind the scene are quite complex, but the matrix essentially transforms all the given coordinates to clip coordinates and transforms the v component of the vectors in such a way that after perspective division is applied, the resulting objects will have perspective. The parameters given define the perspective frustum that the shape where all your visible coordinates should be. Parameter and perspective, dot value, field of view, aspect, another float value. There are all float values. Aspect, the near and far. Specifies the field of view in radians that sets the width of the perspective frustum. Increasing or decreasing this value will give the visual effect of in, and aspect specifies the aspect ratio of your scene that sets the height of the perspective frustum, and changing window coordinates is a good idea. Manage the aspect ratio. Coordinate. The near specifies the near plane of the perspective frustum. All coordinates that are in front of the near plane will not be thrown. Far specifies the far plane of the perspective frustum. Near plane, far plane. What GLM perspective does is again create a large frustum that defines the visible space. Anything outside the frustum will not end up in the clip space volume and will thus become clipped. Perspective frustum can be visualized as a non-uniformly shaped box from where each coordinate inside this box will be mapped to a point in clip space. An image of perspective frustum is seen below. Yes, the perspective looks like this. Orthographic looks like this. We for realistic view it's usually set to 45 degrees, but for more Doom style results you could set it to a higher value. The second parameter sets the aspect ratio calculated by dividing the viewport field by its height. And the third and fourth parameter set the near and far plane of the custom. We usually set the near distance to 0.1 and the far distance to 100. All the vertices between the near and far plane inside the custom will be rendered. Yes, whenever the near value of a perspective matrix is set to I open, we will clip all coordinates close to the camera and give a visual result you may have seen before in video games where you could see through as version of oblique. When using orthographic projection, we don't want to use orthographic projection. I want to use how to put it all together. We multiply it, create a transformation matrix for each of the aforementioned steps M, V, and P, model view projection. The vertex coordinate is then transformed to the clip coordinates as follows. We first multiply it by model, with model, and after with view, and after with projection. Note that the order of the matrix multiplication is reversed. Remember that we need to read matrix multiplication from right to left. The resulting vertex should then be assigned to GL position in the vertex shader, and OpenGL will then automatically perform perspective division and clipping. And then the output of the vertex here requires the coordinates to be in clip space, which is what we just did to transform with transform matrix. OpenGL then performs perspective division on the clip space coordinates to transform them to the normalized device coordinates. OpenGL then uses the parameters from GL viewport to map the normalized device coordinates to screen coordinates, where each coordinate corresponds to a point on your screen. In our case, an 800 by 600 screen. The process is called the viewport transformation. This is a difficult topic to understand, so if you're not still exactly sure about what each space is used for, you don't have to worry. Below, you will see how we can actually put these coordinate space to good use, and enough examples will follow in the upcoming chapters going 3D. Okay, we will find a lot of examples here in the going 3D section. Now that we know how to transform 3D coordinates to 2D coordinates, you can start rendering real 3D objects instead of the lame 2D plane we have been showing so far. Start drawing in 3D. First, create a model matrix. Model matrix consists of transitions, scalings, and or rotations would like to apply to transform all the X vertices to the global world space. Let's transform our plane a bit by rotating it on the x-axis so it looks like it's laying on the floor. Model matrix then looks like this. I will not do this. I will not do this. It gets the model. It does this, does this. I will not do this. Aha. I will not do this. I will not rotate this. Let's do it. I've changed the code a bit. So my current stand looks like this. I applied a little bit transformations for time. So it's rendered like this right now. And yes, let's define I'm defining my matrix here, transformation matrix here. So I will define it here in the loop glm mat for model matrix, which and for 1.0f, and the model matrix will then equal to a rotation matrix, which it by the way which then rotates the model by radians minus 5 degrees, and does it in the y axis. Yes, the model matrix then looks like this. By multiplying the matrix transform into vertex coordinates, we can simply say that the transformation matrix equals to model transformation matrix times model. Oh, please stop translating. Want to translate. I don't want to translate any. I just want to rotate it. How does it? Fast. Still. Better. With this model matrix, we're transforming the vertex coordinates to world coordinates. Our plane that is slightly on the floor. Where are you? On the floor that represents the plane in the global world. Next, we need to create a view matrix. We want to move slightly backwards in the scene so the object becomes visible. When in world space, you are located at the origin 0, 0 to move around the scene. Think about following to move camera backwards is the same as moving the entire scene forward. This is exactly what a view matrix does. Move the entire scene around inverse to where we want the camera to move. Because you want to move backwards, since OpenGL is right, and you have to move. By convention, OpenGL is a right-handed stem. That this basically says is that the positive x-axis is to your right, is to my right, and the positive y-axis is up, and the positive z-axis is backwards. I don't know. Stretch your right arm along the positive y-axis with your hand up top. Let your thumb point to the right. Let your pointing finger point up. Now bend your middle finger downwards. This. This. Discuss how to move around the scene in more detail in next chapter. For now, how the view matrix like this. translate view. Okay. LM. I don't need LM for view. For if afterwards we translate it. Use negative. Push it a bit back. I can type. Push it a bit back. Last thing we need to define is a projection matrix. We want to use perspective projection for our scene, so we'll with this code, but I will type width here. Projection matrix also set, and yes, afterwards we have model view projection matrices. I will simply call it MVP here in the vertex shader animation, or I will simply call it mod4 MVP and call this VP with back for pos and 1.0f. And now I just have to call this MVP set matrix and simply write met for MVP equals projection x small view no? And set it also send the matrix to the shader. Okay. Okay, let's see. Let's see how our fan looks like. It looks like the wanted. So let's go. So far we've been working with the 2D plan and even in the 3D space. So let's take adventurous route and extend our 2D plane to a 3D cube. To render a cube, we need the total vertices, 6 faces, triangles, 3 vertices each. 36 vertices are allowed to sum up, so you can achieve. I guess. I'll not keep doing this. I don't want to render cubes, but we get what we have to do. We also get what we learned, I think, there are queue positions. It will then set the view, model view projection matrices accordingly, and we'll finish this tutorial. Chimera. I am cutting the tutorial here. I'm a bit tired. I will keep doing it at another time. We've come a long way. Let's see. After camera we are done, and we will continue with lightning. To everyone who has been here, a lot for joining. See you later in the camera section. Bye.